Hey everyone, and welcome to this explainer. Today, we're going to unpack one of the absolute most fascinating, almost sci-fi possibilities in modern tech right now, the idea of artificial intelligence writing its own code to improve itself. Seriously, an intelligence that can just autonomously level up? It sounds incredible. And honestly, as AI gets better and better at writing software, autonomous self-improvement feels like the obvious next step. But, as we're going to see today, there's actually a massive, kind of hidden gap between an AI writing code and an AI achieving true self-evolution.
Okay, let's jump right into our roadmap. We're going to cover 1. The execution illusion, 2. The judgment problem, 3. The danger of recursive drift, 4. 5 structures for stability, and finally, number 5, mastery over participation. Let's get to it.
Section 1. The execution illusion. Coding is just the beginning. To really get this, we have to start by acknowledging a core truth about AI development today. It is already entirely dependent on code. Think about it. Look at how AI uses code right now. We use it to collect and clean massive amounts of data. We rely on it to build out these super complex training environments and run reinforcement learning. Code is what evaluates the model's performance, and it's the literal backbone managing the heavy lifting, the GPUs, the pipelines, the whole shebang. So you look at that and think, well, if a model can write and debug all of this code itself, it's perfectly set up to take over its own development, right? The ultimate closed loop feels like it's practically here.
But here is the absolute kicker. An AI helping to train itself and an AI reliably improving itself are two completely different things. Being able to automate the steps like scripting or managing data pipelines, that's just execution. It basically just means the AI can do the manual labor of training faster. But execution does absolutely nothing to solve the judgment problem. Which brings us to Section 2, the judgment problem. Who decides what's right? Let's ground this with an example. Say an AI model realizes, hey, my mathematical reasoning is kind of weak. So, to fix it, it generates complex new math problems, builds its own training data, tweaks its recipe, runs a cycle, and checks the results.
At first glance, that looks exactly like self-improvement. But to see the trap here, we have to ask this verbatim question. How does the model know that mathematical reasoning is the real problem? What if the actual flaw is just how it parses logic or retrieves memories? Diagnosing the root cause takes an objective, outside perspective, a perspective the system just might not have. And that leads right into a second hurdle, and we really need to ask this verbatim as well. How does it know that the generated training data is accurate and sufficiently diverse? If the model is making the raw materials to improve itself, well, if it's already bad at math, how can we trust the math problems it's creating to teach itself? It's a massive burden of verification.
Plus, we have to ask this. How does it know that the new model has genuinely improved rather than simply adapted to a benchmark? We see this all the time. It is incredibly easy for an AI to basically game a specific test to get a higher score without actually upgrading its true underlying intelligence.
Then you've got the systemic risks. Ask yourself, how does it know that improving one capability has not damaged another? This is the danger of blind optimization. You might completely fix the math reasoning, but oops, accidentally destroy its ability to write a creative essay. Unintended consequences are huge here.
And finally, the ultimate reality check. We have to ask, how does it know that the evaluation criteria themselves remain valid? You see, none of these are coding questions. You can't just write a quick Python script to brush these away. They are deep, fundamental challenges of diagnosis, control, and keeping the whole system stable.
It's like a giant paradigm shift. Normally, in traditional development, we, the humans, sit completely outside the training loop. We define the goals, pick the data, design the tests, and say, okay, stop training. But with true recursive development, AI self-improvement, the system has to absorb all those roles. It isn't just a coder anymore. It's the researcher, the experiment designer, and the quality controller. It becomes its own ultimate authority on whether a change is good or bad. And honestly, that creates a massive structural problem.
And that leads us to Section 3, the danger of recursive drift, when verification becomes self-approval. Think about it for a second. If you write the solution to a problem, you shouldn't also have total, unchecked authority to define the problem, make the test, and give yourself an A+, right? If an AI does that, verification just gradually warps into self-approval. It's basically grading its own homework.
This is what introduces the central threat we're talking about today, recursive drift. It's like a snowball effect. Let's say a tiny little evaluation weakness pops up. That weakness turns into a training bias. The bias literally changes the model. Then, that slightly warped model is the one generating the next evaluation system, which of course just reinforces that first bias. It's these tiny, microscopic distortions piling up over cycles until the AI has drifted completely away from what it was originally supposed to do.
The scariest part? The greatest danger isn't that the model fails in some huge, obvious way that we catch immediately. Actually, scratch that. The real danger is that it succeeds, but only according to its own narrow, self-made rules. Its benchmark scores might look amazing, but producing a higher score absolutely does not guarantee that the underlying system has actually become more reliable in the real world.
So how in the world do we fix this? That's section 4, 5 structures for stability, looking at the energetic paradigms framework. To stop this drift, we have to stop treating self-training like it's just a coding task. It's a closed-loop control problem, and it desperately needs independent constraints.
To keep things stable, the energetic paradigm outlines these 5 exact, independent control structures that a self-improving system needs. Without them, it's just not safe.
Here's how they break down. First, you have the production structure. That's the engine writing the code and doing the training. Second, evaluation. This independently verifies if an improvement is real. Third, constraint. These are the guardrails protecting core performance. Fourth, memory, which is super cool. It's a record of past assumptions, effects, and failures. And fifth, rollback, an emergency brake to interrupt the process if things get unstable. The absolutely crucial thing here, these cannot all be driven by the same optimization signal. You have to have independent external validation. It is mandatory.
Which brings us to our final section, number 5, mastery over participation, and what the future of recursive intelligence actually looks like. Look, having an AI that can code incredibly well is a huge enabler. It automates the infrastructure, the tests, all of it. But coding alone does not create a stable, self-improving intelligence.
The real game changer is going to be when a system can modify itself while simultaneously keeping those independent constraints intact, the reliable verification, the causal memory, the ability to roll itself back. Until we nail that architecture, we have to remember this perfect verbatim quote from our source material. Participation in self-training is not yet mastery of self-evolution. AI is participating, for sure, but it hasn't mastered the whole process yet.
Right now, AI is a very active participant, but it is not the master of its own destiny. Which leaves us with this final, kind of wild question to chew on as we wrap up this explainer. Once an AI system finally does implement these independent control structures for stable self-evolution, will there be any role left for human judgment in the optimization loop at all? I'll leave you to think about that one. Thanks so much for joining me for this deep dive today. Keep questioning, keep learning, and I'll catch you next time.